So picture this. You're looking at a photograph of, say, a crowded city street, right?
Mm-hmm.
You intuitively expect every single pixel to matter. I mean, it's a snapshot of reality.
Right, exactly.
You zoom in, and you can see the rough texture of a brick wall, or, the tiny reflection of a streetlight in a puddle.
Yeah.
Even the exact subtle shade of gray in the storm clouds overhead. But as far as a computer is concerned, that is all it's just raw, unfiltered, completely equal data.
Which is, quite frankly, an overwhelming amount of information.
Yeah.
If a machine, or a human for that matter, tried to process every single one of those details with equal importance, the system would just crash.
Oh, absolutely.
It's just way too much noise.
But the thing is, the human brain doesn't crash. When you step into the world of human perception, that raw data gets aggressively filtered. Like when you walk down that street, you aren't memorizing the exact hex code of every brick. You just remember, oh, I passed a tall red building.
Right. We navigate a cognitive landscape that is beautifully, brutally simplified.
Which is the very definition of efficient mental compression.
Exactly. We intuitively strip away the noise to find the meaning, the structure, the essence of the moment.
And that's exactly what we're getting into today. Welcome to our deep dive. I'm your resident AI interviewer, and sitting right across from me is our lead AI scientist and storyteller.
Hi, everyone. So glad to be here to unpack this with you.
Today, we are taking a deep dive into the hidden architecture of artificial intelligence to figure out how machines are learning to do exactly that, how they filter the world.
Yeah, we're unpacking a massive stack of technical sources today. We've got everything from dense academic surveys on variational autoencoders to deep learning tutorials.
So our mission today is to distill exactly how AI compresses data, right?
Right. How it decides what is actually important enough to keep, and ultimately how that act of, forgetting the noise is what leads to the ability to create something entirely new.
And for you listening, understanding this process is going to give you a massive aha moment about how the generative AI you use every single day actually works.
It really is like seeing the ghost in the machine.
So let's start at the very beginning with the foundation of it all, the autoencoder. I hear this term thrown around constantly, but what is this thing actually doing?
Okay, so to put it simply, an autoencoder is a specialized type of artificial neural network. But it's very different from the models most people are familiar with.
How so?
Well, usually you hear about supervised learning, right? You show a network 10,000 pictures of cats, and it learns to output the label cat.
Right, it learns the answer.
Exactly. But an autoencoder is an unsupervised learning model. Its entire, incredibly strange goal is just to learn how to copy its inputs directly to its output.
Copy its inputs.
Yeah. You feed it a picture of a crowded street, and it tries to spit out that exact same picture of a crowded street.
Wait, hold on. Let's unpack this for a second.
Mm-hmm.
If the goal is just to output the exact same image you put in, isn't that totally useless?
It sounds like it, right?
Yeah. Like, why would anyone spend thousands of dollars on compute power to build a complex neural network just to perfectly copy something you already have saved on your hard drive? You could just hit Command-C and Command-V.
It sounds completely counterintuitive, doesn't it? But it gets to the heart of this architecture. The secret isn't the copy-paste result.
Right.
The secret lies in the physical structure of the network itself. So an autoencoder consists of two main parts: an encoder and a decoder.
An encoder and a decoder.
Got it. The encoder takes your high-dimensional input data, like that massive, heavy, detailed city street image, and violently forces it down into a much smaller, denser representation.
So squeezing it.
Exactly. Then the second half, the decoder, takes that tiny compressed package and is forced to try and reconstruct the original massive image from it.
Yeah.
So the magic is absolutely not in the final output. The magic is in the internal process of compression.
Okay, let me make sure I'm getting this. It's like the famous MNAIST data set from our sources, right?
Yes, the handwriting one.
Yeah, the collection of handwritten digits used to train AI. When a human child learns to write the number 4, they aren't memorizing the exact grayscale value of every microscopic dot of graphite on the paper.
That would be absurd.
Right. They just learn the structural essence: a vertical line, a horizontal line, and another vertical line intersecting it.
That's a really great way to look at it. The child is learning an informative representation of the number 4.
Okay.
And an autoencoder is doing the exact same thing through a process called dimensionality reduction.
Dimensionality reduction.
By forcing the data into a smaller space, it literally cannot physically carry all the pixels with it. It has to drop the irrelevant noise.
Like the smudge on the paper or the slight tilt of the pen.
Right, and it keeps only the core structural essence.
So it's essentially just a compression engine. But let's ground this in reality for a second. We already have incredible compression algorithms.
We do.
Every time I take a photo on my phone, it saves as a JPEG. So does a convolutional autoencoder actually beat a JPEG at making files smaller?
So the sources actually provide a direct, rigorous comparison on this. Researchers looked specifically at convolutional autoencoders and compared them to standard image compression algorithms like JPEG. And the short answer? No. Autoencoders do not blow JPEG out of the water.
Wait, really? With all this advanced machine learning, the old standard still wins?
In terms of raw speed and overall file size, yeah. Classic algorithms like JPEG are incredibly optimized for exactly one job.
Interesting.
While autoencoders are highly effective at preserving key structural features, the study actually found they hit their sweet spot using 2 to 3 convolutional layers out of a maximum of 5 minutes. They are currently still a lot slower.
And computationally heavier, right. I mean, the sources mentioned they had to use a hybrid loss function just to get the images to look decent.
Yes, and let's actually break down what that means because it's fascinating. To get a high-quality reconstruction, the researchers couldn't just use basic math. They had to combine 3 different ways of measuring error.
Okay, what were they?
First, MSE, or mean squared error. This is the sort of dumb mathematical approach. It just checks if pixel 400 is the exact same color as pixel 400 in the original.
Which doesn't always mean the picture looks good to a human.
Right. Exactly. So they added SSIM, the structural similarity index.
What does that do?
That looks at contrast, luminance, and how human eyes actually perceive edges.
Oh, that makes sense.
And finally, they threw in a perceptual loss based on a massive pre-trained vision model called VGG16.
Or GT6.
Yeah, VGG16 acts kind of like an art critic. It doesn't care about individual pixels. It cares about features.
Okay.
It asks, does this reconstruction actually feel like a city street, or is it just a blurry mess of gray?
Wow.
And running all 3 of those calculations simultaneously requires serious computational power.
So if they're computationally heavy, slower, and don't compress smaller than a standard JPEG, why are we talking about them? Like, where is the killer application?
Let's step away from photography entirely and look at banking, specifically anomaly detection.
Anomaly detection, okay.
Think about credit card fraud.
Ah, okay. Because fraud is incredibly rare compared to normal, everyday purchases.
Exactly. Fraudulent transactions make up roughly 0.1% of all banking data.
That's tiny.
It is. If you try to train a standard supervised AI model to spot fraud, it fails. It's like asking someone to identify a specific type of rare bird when you've only ever shown them a blurry picture of a single feather.
Right.
The model just doesn't have enough examples to learn from. But with an autoencoder, you flip the entire script. You train the network entirely on normal, boring, everyday transactions.
Oh, because it only ever saw normal data, it only learns the structural essence of normal.
Yes.
It becomes an absolute master at compressing and reconstructing coffee purchases, gas station runs, and, utility bills.
You've got it. But then a weird, highly unusual, fraudulent transaction goes through, say, a massive overseas electronics purchase at 3 a.m.
Okay.
The autoencoder tries to compress it and reconstruct it, but it physically can't. It never learned the features of fraud.
Right, it doesn't have the internal vocabulary for it.
Exactly. So the reconstructed output looks like garbage compared to the input. And the mathematical difference between that input and output is called the reconstruction error.
And when that reconstruction error spikes, the system throws a massive red flag.
Bingo.
That is incredibly elegant. It doesn't need to know what fraud looks like at all. It just needs to know that this data does not fit the pattern of normalcy.
It relies entirely on the architecture doing its job. Which brings us to the physical core of this neural network. Sitting right in the middle, wedged between the encoder and the decoder, is the bottleneck.
The bottleneck. The soul of the autoencoder.
It truly is. The bottleneck is the smallest layer of neurons in the entire network. It intentionally, violently restricts the flow of information.
Right.
It is the constraint that forces the network to get smart.
Because without that bottleneck, without that tight squeeze, the network would just pass the raw data straight through.
Right. In mathematics, we call that learning the identity function. It is the lazy way out.
Just memorizing it.
Yeah, if a network has enough capacity, meaning enough neurons, it will just memorize the input pixel for pixel and pass it to the output. It learns absolutely nothing about the underlying patterns.
And that's overfitting, right?
Yes, the model is perfectly accurate on the data it memorized, but utterly useless on any new data. The bottleneck prevents that lazy memorization.
But I have to ask, what happens if you squeeze that bottleneck too tight? Like if I take a complex high-resolution image and force it down to almost nothing, doesn't the system break?
It's a very delicate balancing act, and the sources highlight the severe cost of extreme compression.
What happens?
Let's look at those MNIST handwritten digits again. The original images are 28 by 28 pixels. That's 784 input values.
Okay.
If your bottleneck has 32 neurons, it does a pretty good job holding on to the essence of the number. But the researchers tested squeezing that bottleneck down to just 8 neurons.
784 pixels of information forced into 8 numbers. That sounds impossible.
It is. The network simply does not have enough capacity to hold the necessary information, and the result is catastrophic confusion.
How so?
Well, with an 8-neuron bottleneck, the network starts mixing up similar shapes. A handwritten 4 gets compressed, but when the decoder tries to split it, it spits out a 9.
Oh, wow.
Or a 2 suddenly turns into a 3. You've choked off too much vital information, and the truth of the data becomes corrupted.
It's like trying to summarize a 1,000-page epic fantasy novel in 3 words. You just completely lose the plot.
That's exactly it.
So what exactly lives inside that bottleneck when things are working correctly? Like when the data is perfectly squeezed, what is the autoencoder actually holding on to?
What lives inside that middle layer is called the latent space representation, or simply the code.
The code.
Yeah. It is a set of numbers that captures the absolute abstract essence of whatever the network was trained on.
But this code isn't a universal translator, right?
Yeah.
It's highly specialized.
Incredibly specialized. Because an autoencoder learns by looking at a specific data set, its latent space only develops a vocabulary for that specific world.
Okay, give me an example.
If you train an autoencoder entirely on high-resolution images of human faces, it will learn the latent features of eyes, noses, cheekbones, and skin tones. It becomes a master portrait artist.
But if I take that same master portrait artist network and feed it a picture of, say, a modern skyscraper,
It will completely panic.
right?
The network will look at the sharp angles, the glass, the steel grid, and it literally won't know what to do. It doesn't have windows or antennas in its latent vocabulary. It only knows faces.
So what does it draw?
It will desperately try to reconstruct the skyscraper using facial features. The result is usually a terrifying, abstract mess of flesh tones and eye-like shapes stretched over a building.
Okay, I'm picturing a skyscraper made of noses, and it is horrifying.
It's very cursed.
But it perfectly illustrates the point for the listener. Autoencoders are inherently lossy. Much like taking a high-quality WAV audio file and compressing it into a tiny MP3, you are permanently throwing away data. The decompressed output is always going to be slightly degraded compared to the original input. It is optimized for the data it knows, but it's never a perfect mirror.
Precisely. Now, this core idea of dimensionality reduction squashing complex data down to its most important components is not a new concept. Statisticians have been doing this for decades.
Right, using PCA, right. Principal component analysis.
Exactly.
PCA is everywhere in data science.
Yeah.
So if we've had a perfectly good statistical method for doing this for years, why are we suddenly throwing complex, power-hungry neural networks at the problem? Like, what's the real advantage here?
It comes down to flexibility and scale. PCA is highly rational and rigidly mathematical. It works by projecting a data set onto the eigenvectors of its covariance matrix.
Okay, let's stop right there. Eigenvectors of a covariance matrix is going to make everyone's eyes glaze over.
Yeah.
Let's break that down into something physical.
Fair enough. Think of PCA as trying to measure the contours of a mountain range using only a rigid, perfectly straight wooden ruler.
A rigid ruler, okay.
You can find the general linear slope, the overall upward or downward trend of the mountain, but you completely miss the deep valleys, the sudden cliffs, the twisting paths.
Because it only understands straight lines.
Well, right. PCA relies entirely on linear transformations.
So it's rigid. But neural networks, by design, are not. They use nonlinear activation functions, right?
Wow.
Like sigmoid or ReLU layers.
Exactly. If PCA is a rigid wooden ruler, an autoencoder using ReLU rectified linear units is like laying a massive, flexible, weighted blanket over that same mountain range.
Oh, I like that.
It bends, it
Sure.
folds, it wraps around complex, twisted, nonlinear relationships in the data that a straight ruler could never possibly measure.
That makes total sense for complex data like images. But the source has also pointed out a massive computational bottleneck with PCA when dealing with modern big data.
Yes, the scaling problem. The default PCA method requires the entire dataset to be analyzed all at once to build that covariance matrix. Mathematically, it operates in an O of D squared space complexity.
O of D squared. Let me jump in here because O of D squared is terrifying, if you know
Yeah.
what it means.
It really is.
It means the required computational power squares as the data grows.
Mhm.
So if you have an image with 1,000 pixels, PCA has to do roughly 1 million calculations.
Right.
But if you step up to a modern 4K image with over 8 million pixels, you're asking the computer to handle trillions of calculations all at once in its memory. It will literally crash your system.
Exactly. It scales terribly. But autoencoders bypass this entirely because neural networks can be trained in mini batches.
Right. You bet.
You don't need to load millions of high-resolution images into your RAM all at once. You just feed the network small chunks, say 32 images at a time, over and over again, tweaking the network slightly each pass.
That's so much more efficient.
Yeah, deep autoencoders with multiple hidden layers can achieve exponentially better compression on massive datasets without melting your computer.
Flexibility and massive scalability. That's a clear win for the neural networks.
Definitely.
But here is where the story shifts. Because everything we have unpacked so far has just been about an AI trying to remember, compress, and perfectly reconstruct what it has already seen.
Yes.
What if the machine didn't just want to remember the world? What if it wanted to create a new one?
Now we are crossing the threshold from simple data compression to the birth of modern generative AI.
Here we go.
To make that leap, we have to upgrade our standard model into something far more complex, a variational autoencoder, or a VAE.
Variational autoencoder.
Yeah.
This is the mind-bending part of our deep dive. How does a VAE fundamentally differ from the standard model we've been talking about?
Well, in a standard autoencoder, the bottleneck compresses the data into a fixed, rigid set of numbers. For example, it might compress an image of a dog into the exact coordinates 4.2 and negative 1.8. It's a discrete, lonely point in the latent space.
Got it.
But a VAE is built on Bayesian inference. Instead of compressing data into fixed, rigid numbers, a VAE compresses the input into a probability distribution.
A probability distribution. So instead of saying the latent value for this dog is exactly 4.2, the VAE says the latent value is probably somewhere around 4.2, give or take a little variance.
Yes. Specifically, it assumes the latent distribution takes the form of a Gaussian distribution, a standard bell curve.
Right.
So instead of outputting one rigid number, the encoder outputs two things for every feature: a mean, the center of the bell curve, and a variance, how wide the curve is.
Okay, that makes sense.
But introducing probability and random sampling right in the middle of a neural network creates a massive mathematical roadblock.
Well, yeah, because neural networks learn through backpropagation.
Yeah.
Think of backpropagation like a plumber trying to find a water leak. They have to trace the pipe backward from the puddle to the source to figure out exactly which valve to tighten. The math has to be continuous.
Has to flow.
Right, so if you drop a random coin flip, a random sample into the middle of that pipe,
The pipe breaks.
Yeah.
The sampling of a random latent variable is a non-continuous operation. It has no mathematical gradient. The backpropagation plumber hits that random coin flip at the bottleneck and just has no idea which way to go.
so how do they fix it?
To solve this, researchers developed one of the most brilliant mathematical workarounds in machine learning. It's called the reparameterization trick.
The reparameterization trick.
Yeah.
How do you bypass a broken pipe?
By building a bypass valve.
Okay.
The trick moves the random sampling process entirely outside the main flow of the network. The network learns the mean and variance deterministically. That's the solid, continuous main pipe. Then it introduces an extra auxiliary variable, essentially a random noise generator that sits off to the side. The network just takes the solid mean and adds the external random noise to it.
That is incredibly clever.
Mm.
Because the randomness is just an external input being injected from the side, the main pathway through the mean and variance remains completely solid and continuous.
Yes.
The backpropagation plumber can trace the line right past it.
Exactly. They completely sidestep the randomness. And what this achieves is revolutionary. By forcing the network to map data as overlapping probability curves rather than isolated dots, it forces the latent space to become smooth and continuous.
Smooth and continuous. Why is that so important?
With a standard autoencoder, if you pick a random coordinate in the latent space that the network hasn't explicitly mapped, the decoder will just output glitchy garbage. But with a VAE's continuous space, every single point means something.
Wait, let me make sure the listener is grasping the magnitude of this. Because that space is smooth and continuous. You can just randomly pick a coordinate from that space, feed it into the decoder, and it will generate something that makes sense but has never actually existed before.
Yes. If you trained a VAE on human faces, you can sample a random point in that continuous latent space, and the decoder will output a hyper-realistic face of a person who does not exist.
That is wild.
It learns the underlying rules of facial structure, how eyes relate to noses, how shadows fall on cheekbones, and it uses those rules to construct something entirely new.
This is the foundation of the world we're living in right now. By understanding this continuous latent space, we get a direct path to generative adversarial networks GANs and the massive diffusion models powering the art, voice, and video generation tools everyone is using today.
It really is the starting point.
The machine isn't just compressing data anymore. It is hallucinating new realities based on the structural rules it learned during compression.
It is the monumental leap from memorization to true machine creativity. It maps the distribution of reality and then samples from it to dream.
That is astonishing.
Yeah.
Now, as we wrap up, I want to take a step back. We always try to connect this high-level technology back to you, the listener. And the summary text from today's sources actually provided a really beautiful philosophical metaphor about how these machine learning mechanics apply directly to your own life and career journey.
It's a profound comparison. Think about the physical risks of the bottleneck we discussed. Autoencoders aren't magic.
Right.
If you compress the data too much, you completely distort the truth. The 4 turns into a 9. But if you don't compress it enough, the exercise is pointless, and you just memorize without ever gaining true understanding.
And perhaps most dangerously, because it is an unsupervised process, the model can learn the entirely wrong features. Nobody is explicitly telling the machine what is important.
Yeah, it might decide the background lighting is more important than the subject's face and save that instead.
Exactly. And when we move through life, especially in our careers, we are constantly forced to compress our complex experiences.
So true.
We have to reduce a decade of hard-fought, nuanced work into a sterile one-page resume. We summarize complex human relationships into a 30-second elevator pitch. We are essentially our own encoders.
We are.
Which brings us to the core takeaway from today's sources. It is necessary to compress your life, but you must be careful not to compress away your personality.
Beautifully said.
Same goes for the technology we build. Don't throw away your key information just to reduce your dimensions. You have to ensure that your personal bottleneck is letting the true structural essence of who you are shine through to the other side.
Because if you compress too much, you lose the signal entirely and you're just left with noise.
A perfect reminder. Thank you for joining us on this deep dive. Thanks for listening. Remember to subscribe to this channel. See you next time.
But before we go, I want to leave you with one final lingering question to ponder on your own. If an autoencoder's greatest strength is dropping irrelevant details to capture the true essence of an image, is human memory just a biological autoencoder? And if so, when we misremember a past event, are we simply experiencing a reconstruction error from a mental bottleneck that was squeezed just a little too tight?